worked on for many years and have recently completed the publication of this monumental series. And this really, George's work, we've heard some of the work of Swagers and harmonic Moss forms, and the work of George and others really set the stage for Swagers to make these kind of, Swagers and Brunier and Funke to make these kind of discoveries, and really has led to a revolution in the study of Mach theta functions and Mach modular forms, and just really has been indispensable in this subject for many years. All right, so George, we're ready for you to take it away.
Okay, thank you, Larry.
Yeah.
So, someone from Brussels saying that you need to record this.
Yes, it's recording now.
Okay, so I regret that I'm not in Nashville. My trip back to State College from the conference, the CBMS conference in Texas, was an absolute nightmare. And I spent much of Saturday night trying to find a place to stay in Philadelphia before I could get home. All flights were booked, all rental cars were booked. And I believe that as a result, I have this very bad cold. I tested myself for COVID this morning and it was negative, but nonetheless, I'm really somewhat under the weather. So my voice is also about an octave lower than it usually is. So you'll have to bear with me. In fact, I think I would have done better to have gone straight to Nashville instead of trying to get home in order to go to a conference this week, which I will have to only Zoom into. I also want to apologize for the fact that this is not the first time I've given this talk, but I can mitigate my sins here by saying that if this conference had been held in 2020, as it was scheduled to do, this would have been the first time that I'd given this talk. Also, I fear that this talk is what I call down in the weeds. And generally, I dislike talks that are down in the weeds. So why am I giving one of that nature? In this case, I think that it is the only possible way to really make a convincing case as to how Ramanujan might have discovered the Mach theta functions. So I hope to at least mitigate the weediness of the talk by starting out with a little history and then an example that illustrates the method that is involved. Then I want to turn to a number of formulas in the Lost Notebook to show that Ramanujan had to have been a master of this method. And then I want to get to the main portion of my talk, which is to try to lead you from things that Ramanujan said in his last letter to Hardy that would help us understand how he got to the Mach theta functions. So here is the last letter to Hardy, at least part of it. And I don't really expect any of you to be able to read what is on the screen, except I will retype this. In particular, at the top of the screen, you see A and B, and I'm going on the next slide to put this into form where I think you can actually see what it says. So right at the top of that letter, Ramanujan says, if we consider a theta function in the transformed Eulerian form, and so what he means by the transformed Eulerian form is we would now refer to as a Q-series formulation. And he has two of these series. The only difference between A and B is that the denominator is of what appears in B is squared in A. I will mention what the infinite product form of these series is in a moment, but he says we want to determine the nature of the singularities at the points basically what he's referring to are the roots of unity on the unit circle. And he says, we know how beautifully the asymptotic form of the function can be expressed in a very neat and closed exponential form. Basically, he's referring to the radial approach to these singularities from inside the unit circle. And he says, I want to point out that the nice behavior of A and B results from the identities that you see on the screen. The first has been attributed by Hardy and Ramanujan to Euler. However, I have searched a good deal in Euler, although if those of you who are familiar with Euler's collected works realize that they fill a large portion of a library shelf. And so whether or not this series is there I have never found it there. Also, it is not something that naturally occurs to you when you are first discovering this sort of topic, as Euler was. And so I think that really A should be attributed to Jacobi, because he needed this and a generalization of this in his proof of the Jacobi triple product identity. B is the familiar first Rogers-Ramanujan identity. And here is the first of many typos I see. The little a at the bottom of the screen, the little a on the left-hand side should be a capital A, but this is the standard Q-Pochhammer symbol. Ramanujan then proceeds to speculate about the possibility of functions that, one, behave beautifully near the unit circle in the same way that the modular forms, which are the right-hand sides of A and B, or modular function in the case of B, the way that they behave near the unit circle. And two, are not theta functions, i.e. modular forms. While Ramanujan says he has not proved the existence of such functions, he nonetheless lists 17 functions, which he firmly believes are these new functions, which he terms Mach theta functions. The first three functions that he lists are listed here. And here's my next typo. Namely, the series that you see at the top of the screen is identical with the series that I had in A. And so the thing wrong here is the minus sign that you see in the denominator products. All those minus signs should be plus signs. The next two functions I think I have written down correctly. Ramanujan did not use a subscript 3 on any of these functions. However, Bruce Barrett and I, in trying to distinguish the various functions of third, fifth, and seventh order in writing about all of the identities that he did, felt it was important to put subscripts here because Ramanujan basically uses the same notation for third order functions and fifth order functions. And so the 3 here is to emphasize these are what he called third order Mach theta functions. And he asserts that these functions satisfy the identity that you see at the bottom of the screen. So the first two expressions are linear combinations of these functions, f, phi, and psi. And the final expression is quite clearly the first thing in the parentheses is the theta 4 series. And the second thing is this infinite product of 1 plus q to the n. So the right-hand side is a modular form, so that linear combinations of these functions add up to a modular form. But here is the real question. What would have given him the idea that such functions might be possible? Second typo, that capital F should be a little f. In addition, why would you latch on to these 3 functions to be, so to speak, the starting point for your considerations? So I want really to emphasize this slide more than anything, because if you're just given the classical theta functions that that exist that had been fully explored by the time Ramanujan was writing this material in 1920, so that there were the understanding of modular forms and the elliptic theta functions, all of that was clearly understood, but it's not really a natural question to say, suppose that something was sort of halfway into this world, but not the same as this. Indeed, in his last letter to Hardy, he stresses that the false theta functions of Rogers are not, do not have this wonderful property that the theta functions possess in terms of their behavior near the unit circle. So this is the mystery that I at least am trying to give a plausible explanation for this morning. I should be a little humble and recognize that the only other time that I believed I had explained something in Ramanujan's lost notebook, that I had, so to speak, found the idea behind the whole sequence of identities that he listed. I presented this at the 100th Centennial Conference for Ramanujan, and afterwards, K.G. Ramanathan came up, rather than embarrass me in front of the gathered throng, came up after my talk and pointed out that probably what I said wasn't accurate. Well, what I said was mathematically true, but was not the best guess for how he did this. So I'm certainly willing to admit that the guess this morning may not be right, but do keep in mind, it is a real leap to think that such functions might exist if you are working in 1920. So Ramanujan, although this is called the Heine transformation, and it is a classic which was known to Heine and proved by him in the mid-19th century, but I believe that Ramanujan knew how to prove identities like this all over the place. That will be the second portion of my talk. He didn't prove this formula in the Lost Notebook or anywhere else, but it illustrates, the proof of it illustrates the method that I am describing this morning. The proof of Heine's transformation and subsequent identities considered by Ramanujan rely on a very simple formula, which is this Q, basically known as the Q binomial theorem, and is easy to prove just by analyzing it, the functional equation as in Z. There's a first order functional equation in Z for this infinite product. And when you try to write that functional equation out using an infinite series, the coefficients of the series are what you see on the left-hand side of this equation. Notice, again, my umpteenth typo in the bottom of the screen. The finite product, the little n, capital N are the same thing. So the little n should be a capital N, but you often rewrite a finite product as a quotient of two infinite products, which seems a little counterintuitive, but nonetheless, you will see precisely how it works. So here's the way the proof of Heine's transformation goes. I'm going to rewrite the BQ sub n and the CQ sub n in terms of these infinite product quotients. And that will mean that I will have the two infinite products involving B and two infinite products involving C, each of them produced by the identity that you see at the bottom of the screen here. So now we have the infinite products for B and C inside the series, and we rewrite that using the Q binomial series that you saw on the previous slide, so that that quotient of infinite products becomes this series. And now we interchange the order of summation. There are certain constraints that you need on the parameters involved in order to guarantee that the change of summation is valid. but those are easily determined. And now you have the n sum on the interior, and it too is a Q binomial series. So you sum it up, and now you have the infinite products, and now you reverse engineer things by taking those infinite products and replacing them by finite products, with the infinite products coming out front. And lo and behold, that's Heine's transformation. The thing you see from the top of the screen to the bottom is precisely the Heine transformation. So let me summarize again. What happens is you replace the finite Pochhammer symbols by quotients of infinite products. You expand the infinite products using the Q binomial series, interchange the order of summation, and then reverse things by then replacing infinite products by first getting infinite products and then replacing the infinite products by finite products, and Heine's transformation has popped out. So, well, as I say, this formula did not appear in Ramanujan's notebook. A more complicated formula that you see here, I'm sorry about the dagger. The dagger is meant to imply that the top line is equal to the bottom line. And this looks a lot like this is, so to speak, taken straight from the lost notebook using Ramanujan's variables. It looks a lot like the formula that you just saw. And indeed, the proof of it goes exactly like the formula that you just saw. And the only thing that slightly changes is that there are some squared values of Q, as you see there, and there's some subscripts, excuse me, that arise here in this series, but the method of proof is exactly the same. Here's another formula that is very similar to what you saw in the previous slide. The quadratic exponent that arises comes from limiting cases of the Q binomial series. Maybe I should. There we are, the Q binomial series. If you replace if you replace Z by say Z over A, and let Z go to 0, you will get a quadratic exponent on the left, and you will only have a numerator product on the right, since Z will have gone to 0. So that's where these quadratic exponents arise. And so there are countless ones of these. Some of the ones that I've just shown you are on a page like this from the Lost Notebook. Notice that Ramanujan, nothing is ever proved in the Lost Notebook. There are just formula after formula after formula, except occasionally there are pages that are completely sort of scratch paper type computations, but the majority of pages have a formula, and then there's another formula, and then there's another formula. And they are not necessarily related to one another, although on this page, several of them are. And indeed, one of the formulas that you saw on that page is of this nature. Again, the proof of it is exactly like the proof that you saw of Heine's transformation. Here's another example. There's a missing power of Q in the series on the left. Otherwise, the series on the left would not converge. But basically, once you put the power in, it's there. Here is an example where the series split up into two series on the right. So I want to show you how the proof of the last identity would go, because it is illustrative of what we will see in trying to get to where Ramanujan saw the Mach theta functions. So you have a series like this, and now what Ramanujan does is to rewrite that product in the numerator, the AQQ sub n, as a quotient of infinite products. And then you expand the infinite product inside the series by the Q binomial series, which what you see what is there. And then you interchange the order of summation and sum the series on n, which is summed according to the limiting case that I just told you about. And now you have a problem because this product has a very different quality to it depending on whether m is even or odd. And so you have to split it into two cases. Once you split it into two cases, then you are able to use the factorization that we described earlier, which allows you to pull the infinite product out and to rewrite the series using an infinite product. And then you can pull that infinite product out of each series and you have precisely the formula that Ramanujan have. The reason that I went through this one explicitly is to show that there are variations of what you can do, that not everything goes just nice straightforwardly the way Heine's transformation does. There are sort of quirks and twists that are necessary, but examples of them occur throughout the Lost Notebook. However, the sequence that I'm going to take you on for the discovery of the Mach theta functions is not anywhere in the Lost Notebook or in Ramanujan's last letter to Hardy. So anyway, you can fix all these things up to get the exact formula that Ramanujan had in the Lost Notebook. So now I want to head into the actual method of discovery. So this is where, as I say, we get down into the weeds, but the methods that you have seen up to this point should sort of at least prepare you for for what is going to happen. So this is formula A in Ramanujan's notation in his last letter to Hardy. And he also has this in the Lost Notebook. And Hardy and Ramanujan discuss this series at length in their paper on the asymptotic formula for P of n. That paper is a rather interesting one to read because it builds up very gently to the use of complex analysis to determine the exact formula for P of n. And they get an approximation by studying this series. So Ramanujan was quite familiar with this series. So the first thing that Ramanujan might think is, can I apply the methods that I have developed in the first part of this talk that I shown you that he has? Can you apply it to this series? And the answer is, as it stands, no. Because with a q to the n squared in the numerator, what he needs in the denominator is a product of the form q squared sub n. That would allow him to then utilize the method of utilizing the q binomial series, but he doesn't have that. So what he needs is, as I say, q squared sub n in the denominator. So here we go. Wait a minute. Let us put it in. So you put in q squared sub n. So that, of course, factors into q sub n times minus q sub n. And so you have to cancel that out in the numerator. And so you put minus q sub n in the numerator to get things back to the way they were. And now you have this quotient that you see of two of these finite Pochhammer symbols. And so you apply the method that we applied in Heine, and you see this taking shape. And now you can actually rewrite those quotient of products as this series using the q binomial series, except from the q binomial series. And now you move the n series in and you sum on it. And now you have the same problem that we had in the previous example. You have an infinite product with a q squared variable or q squared modulus and a q to the m plus 1. So it's very important to deal with whether m is even or odd. And so we proceed just as we did in the example to rewrite this so that the infinite products can be factored out, which we have here, and we do the factorization in the next slide. And now we have this series, two series now that are where the denominator has the subscript 2m or 2m plus 1. But you can split those into two Q Pochhammer symbols on base q squared. Namely, you factor out all the terms with even exponent in the first series, giving you q squared sub m, and the terms with all odd exponents giving you q squared sub m. And that's what I've done in both series, but I've done something else which seems a little bogus. Namely, I've put a q Pochhammer symbol with 0 in it in the numerator, so that this Pochhammer symbol is 1. So, but the reason I put it in is I want you to see that both these series are now instance of the Heine transformation, or the Heine series that I showed you initially. And so one has then all you need to do. We've seen Heine's transformation, and each of the two final series are of that form. The only difference is that the base q is now replaced by q squared. So we can use this transformation on these series. And once Heine has been applied and the simplifications have been made, it all boils down to this. And so I mentioned in Texas that the thing that drives me crazy about giving a talk from a computer screen instead of the old overhead projector is that with the overhead projector, you know what's on the next slide. And I'm not sure what's on the next slide here. So I'm going to have to just, okay. So basically you can rewrite this now, because the first series is phi sub 3 of q with a minus q involved. And the second series is psi 3 of minus q. And so the two series on the right are phi 3 minus q, 2 psi 3 of minus q, and everything else is the on the left, what you're left with is a pure modular form. I claim that this may well have been the aha moment, because the phi 3 of q is going to be bounded when q tends to certain roots of unity that I've listed here. And the second one is going to be bounded at different roots of unity, which I've listed here. Thus, at certain roots of unity rho, phi 3 of minus q remains bounded as q tends to rho. I mean, wait a minute, whoops, I'm going in the wrong direction. So for example, just to make very clear what's happening, if you look at phi 3 of q, when q tends to 1, this series, you have to be careful in letting q tend to an essential singularity. But on the radial approach, as I will actually illustrate, subsequently, the limit as q tends to 1 is exactly what you would think it would be, namely the summation 1 over 2 to the n. In other words, it remains finite. And at others, it has to behave like this because the psi of q remains finite, okay? So he's got an identity here where a significant portion of the time, phi 3 of q has to behave exactly like the modular form on the left-hand side of this identity because the thing paired with it is tending to a finite value as q tends to that root of unity. And I contend that in looking at this identity, Ramanujan's so familiar with all of these things, especially with the radial approach to the unit circle, which permeates the paper with Hardy and Ramanujan. He would have seen this instantaneously, I contend. Of course, he wrote down nothing of what I have said so far. So that's why I say it may well have been the aha moment. But the point is that assuming that he saw this, then everything is worth investigating because here he has explicitly staring at him from the page functions that behave at certain roots of unity exactly like modular forms with its big O of 1 error, and at other roots of unity remain bounded. So, as I said, these bounded limits as q radially approaches unit are easily proved, and so I'm just going to give you an example of how you prove it. I mean, you just can't set q equal to 1 and get away with it. You really have to split the series up from 1 to capital N and capital N plus 1 to infinity. Then as q tends to 1 in the first series, it automatically you sum. And the second sum, you can easily bound each term by q by 2 to the minus n. That n in the last line should be in the exponent. So where do you go from here? Well, excuse me. So way back at the beginning, another great thing about overhead transparencies is that I could pick up the transparency that had F3 of Q on it. Whereas now I just have to tell you it again and remember that if the minus sign here was removed, that's what we started with. That was where Ramanujan started, just seeing where it would go if you had the actual series for the generating function for P of n. We asked ourselves where it would go using the methods that we had seen earlier, and we got to this wonderful formula that you saw on this slide, namely the thing right in the middle of the slide. But it's quite clear that if you started with this, you could play exactly the same game as before, except the signs would be changing throughout. And with the signs changing throughout, what you will wind up with is that F3 is phi 3 minus 2 psi 3. And from here, remember that Ramanujan in his last letter stated three identities relating F3, phi 3, and psi 3 to a modular form. You can deduce those identities from this identity and the one that I just showed you for phi 3 and psi 3. You can easily move from here to those identities. It's not quite clear why he didn't write things the way I've said. He never wrote things this way, but it's easy to deduce what he did write from the things that you've seen deduced this morning. So his next page, or the material beyond what I showed you just now, he goes on to what he calls fifth order Mach theta functions. Well, here's a list of the results he found. And he has identities like this in the Lost Notebook. Indeed, that was one of the ones that we described earlier. And if you set A equal -1, you get things like this. And what you have here are instances of his fifth order Mach theta functions. In other words, he has identities that are more general than the identities that he had in the last letter, because these formulas imply certain of those identities. And this, for example, is one of them, setting A equal 1 in A equal 1 in this, A equal -1 and A equal 1 give you examples of his fifth order Mach theta functions. Well, he also, at the end of his letter, I hate to cycle back to it, but I think I will. Right at the end of his letter here, he lists 3 functions. He calls them seventh order Mach theta functions, and that the letter is cut off at the bottom, but the third one resembles very much the series representation of the other 2. And after that, he writes down, these are not related to one another. Sincerely yours, Srinivasa Ramanujan. And that was the end of his last letter. And so what about the seventh order Mach theta functions? They appear nowhere in the Lost Notebook. And indeed, what you find in the Lost Notebook at the bottom of one page. So Frank Garvin in his PhD thesis showed that Ramanujan had a formula which would prove all of the Dyson conjectures about the rank for the fifth or of related to the partitions where the parts are, where the number being partitioned is congruent to 4 mod 5. There's an identity there that is, in effect, the key identity that Atkin and Swinnerton and Dyer used to prove the conjectures of Dyson. And so Ramanujan, however, did not look at all at any of the combinatorial implications of his work, nor did he prove things. He only wrote down this massive master formula, which took Atkin and Swinnerton and Dyer a significant amount of effort to get hold of. And this proves or establishes the Dyson rank conjectures. This at the bottom of the next page, after the page that Frank Garvin explained so fully, there is the left-hand side of what should be related to the seventh order Mach theta functions, but there is no next page. In other words, the pages are all loose in the Lost Notebook, so we are uncertain what, there's this equal sign at the bottom of the page and then nothing related to it on the page that happens to be next, nor is there anything like it throughout these pages, which only means that maybe the relevant page was lost, or maybe he didn't know how to do the next page. All we can do is speculate. But in any event, I believe that what you've seen this morning is a plausible way that Ramanujan would have found the first Mach theta functions. And obviously, once he'd found such functions, seeing what with his method would yield other such functions was a natural step to take. Of course, it should be pointed out that in his last letter to Hardy, he left out a bunch of things. And in Watson's second paper, which he deals with the Ramanujan's statements in his last letter on the fifth order Mach theta functions, Watson conjectures that you can't really ever get to the Mach theta nature of these functions the way you did with the third order functions, because Watson conjectures that the relevant formulas relating these to a Pell-Lerch series don't exist. And so one can only speculate that Watson never seriously looked at the lost notebook, even though he had it in his possession, because Ramanujan writes down the exact formulas that would allow the discoveries that later were made by others, by Bringman, by Zonders-Zwegers, etc. There are the formulas that make it clear that you can do this, and Watson, in writing about the fifth order functions, conjectures that they don't exist. So in any event, I apologize for the weediness of this talk, but I hope that you by that much weediness, you have gotten an idea that maybe this is how Ramanujan's both technical skill and genius led him to the Mach theta functions. Thanks very much. Thanks for putting up with this on Zoom. Thank you.
Well, thank you very much, George, for that enlightening talk. Any questions from the audience? And again, I'll emphasize that the Zoom people, we can also see your comments, so feel free to chime in or write a comment as well. Well, I have a historical question, George.
Okay.
Your initial at the Ramanujan 100 conference, where you proposed how he might have found them.
Yes.
How does this approach fit? Is it sort of similar, or is it differ quite a lot?
So here at that conference, Ramanujan had a page of continued fraction identities, seemingly unrelated to another. But on a subsequent page, there is a master formula for continued fractions, just in the middle of stuff unrelated to other things, from which you can derive everything on the page that I was citing. And so my conjecture was that he used this master formula to prove these results. Ramanathan, after my lecture, came up and said, well, maybe, but on the other hand, Atlee Selberg, in a paper that he wrote when I think he was 18 or something, related to Rogers-Ramanujan type identities, had a number of continued fractions that he basically proved using a very straightforward functional equation method that Ramanujan also would have been familiar with. And if you used his master identity, you had to know certain Rogers-Ramanujan identities, some of which are not in the Lost Notebook nor in Ramanujan's other writings. And so Occam's razor suggests that Ramanathan was correct and I was wrong. And so I've always been reluctant to say that here's how Ramanujan thought about things, because after working on his mathematics, going through the Lost Notebook with Bruce Baird to provide proofs of everything, I'm quite convinced that A, many of his formulas are not, we do not prove them the way he proved them. And B, he had certain insights. I won't say he had rigorous proofs, although I suspect that if we had his insights, we could definitely construct out of them rigorous proofs, because as everybody in the audience knows, in many research projects, there comes a moment when you see, bingo, that's how it is. This is how it goes. You haven't done all the lemmas, and there may be a few problems in the lemmas and so on, but you see how it goes. And I suspect that, in effect, I would guess that he had something that could be easily turned into a rigorous proof, but that he did not ever communicate. The only thing I will say about that is that there's a reprint that Oliver Atkin had from that Ramanujan, that F.H. Jackson, and the reprint of F.H. Jackson a mathematician contemporaneous with Ramanujan, in which Jackson says, this formula is related to the Rogers-Ramanujan identity, so I sent it to Ramanujan, and he explained to me how he discovered the Rogers-Ramanujan identities. Well, that letter that was sent to F.H. Jackson is lost. So Ramanujan did at least once try to explain how he found things, but it's never, the letter that contains that is lost. So we are stuck with mysteries, but I do suggest that trying to at least guess how he thought of things is a valuable enterprise if it is not necessarily how he did think of things.
Great. Thank you. Robert Schneider has a comment in the chat. I'm not sure if everyone can see it. And Robert says that it's very interesting to see how the mixed modular form behavior at roots of unity arises naturally.
Yes, I mean, that's quite, that identity where I said this is the aha moment. If he ever did get to that stage, and he was always looking, I mean, the method that I've described that he used, I've just given you a sample of things that where he clearly was using that method, and it would be most natural for him to look at it in the way he did. But if he got to the formula that I say, the aha moment, he would have seen the calculations that I described in some detail there. I'm confident of that.
Okay. Any other questions? Oh, Paul, or no, yeah.
Shout it out.
Yeah, or maybe shout it out and I'll repeat it. I don't have to run my phone.
Well, it's a somewhat technical question, but at some point in your talk, you started with this QQ sub n in the bottom, and you needed a Q squared. It's Q squared.
Yeah.
In the bottom.
Yes.
Why? Yeah. I mean, yeah. Well, why was that?
Okay, let me go back to where that was. So look, so the point is that if you want a limiting form of the, oh, nuts. So here's the Q binomial series. So if I replace A by A over Z and let Z go to 0, the numerator in the series will go to Q to the n choose 2. In other words, it'll be n squared minus n over 2. If you want an n squared in the numerator, you replace Q by Q squared, and then you will have a Q to the n squared in the numerator, and a Q squared sub n, and you can utilize this identity in order to transform things. But you can't, if you have Q to the n squared in the numerator and a Q sub n in the denominator, that's effectively like the Rogers-Ramanujan series. You can't apply this very elementary formula to it, so that when you're looking at this, if you're going to apply that at all with that Q to the n squared sitting there, you have to get that factor in the denominator. You can't get started without that factor in the denominator. So how do you get it in the denominator? You put it in, and then you cancel out what made it Q squared from the QQ sub n. So this is the first step. And this is a step that Ramanujan would have had. If he had started this is how he would have started. There's no question about that. And once you get to this, then you can just go on and see where it goes, because on it goes. I mean, once you are at this point, things just snowball. There is only one thing to do at each stage. At each stage, interchange the summation, etc. So there's only one thing to do, and it has to be this particular change.
Great. Drew Stills has a question in the Zoom. Drew asks, given all of the Rogers-Ramanujan type identities and false theta identities written down by Ramanujan, would you speculate that Ramanujan on some level understood the Bailey pair machinery?
I don't think so. I mean, Rogers certainly. I mean, the Bailey pair machinery is 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 polished up by Bailey, and that's why I have in my writings called it the Bailey pair stuff, because the full generality of it first appears in Bailey's work. But Rogers knew Bailey pairs for the special cases of the parameter when A is 1 or A equal Q. But you don't see that in anything that that Ramanujan wrote down. You see basically formulas that he got even when he was looking, even in the joint paper with Rogers, which was really not a joint paper, but a collection of letters sent back and forth between Rogers and Ramanujan and sort of put together by G.H. Hardy. Even there, you see the functional equation proof of the Rogers-Ramanujan identities. So if he knew Bailey pair machinery, he never gave it away. He never hinted at it. He did write down many formulas that can be proved with Bailey pair machinery, but he didn't say that. So I don't see it there. But there are lots of things. Most of what I've said this morning about him getting to the aha moment is not anywhere in his work either. So I will rate my last comments at a 30% confidence level.
All right. Well, I forget which famous mathematician said this, but there's a famous anecdote about one of the great mathematicians saying that I only show the leaves of the tree and I remove the branches.
Now, Ramanujan was very good at removing branches.
Sometimes it's best to it makes them seem a little more magical and mysterious if you only show the last thing and not how you got there. But it can also be useful for others to see how you got there, but less magical.
Yeah.
Yes, Frank has a question.
Can you hear me, George?
I can hear you, yes.
Have you looked carefully at the calculations in the lost notebook that sort of look like a mess? Whether there's a connection with ranking a crank for mod 7 and 11?
I've not seen, look, I have looked at them and I have sort of tried to make sense of some of them.
So, for example, if you look on page 70,
yes.
lost notebook, I don't know if you've got it in front of you.
So I think I could gather it up. Let me gather it.
Well, you know, people have these pocket constitutions or something. Somebody needs to get a pocket lost notebook or something. Keep in your back pocket with all that.
That's what he's talking about. Page 70.
Well, George is looking. Robert Schneider also has a comment about the trees, and he says that Ramanujan also removed the low-hanging fruit, unfortunately.
There's page 70. So if you can make sense of it, Frank, you're a better man than I.
So if you look on the right-hand side of that page, you'll see a column of pairs of integers.
Yes.
Those pairs of integers actually correspond to the infinite products when you do the 11 dissection of the crank.
Okay. Well, indeed, yeah. Indeed, there are lots of 11s here sitting there. I see that.
Right, and you see that there's I think there's a q to the 6/11 missing.
Okay.
So
I can believe.
I don't know if you've looked at this, but this looks like the crank mod 11.
It could well be.
So anyway, so I don't know if you.
Both 70 and 71 have a bunch of 11s on them, so I don't know.
So I don't know if you.
Anyway, I've not looked seriously at these pages. I mean, I've looked at them, but they're really perplexing.
those pairs of integers correspond to infinite products.
Yes, I'm sure that's true. Yeah.
So, and their ratios of infinite products, and those are the exact same products that occur when you 11 dissect the crank function, mod 11.
Okay.
I believe.
Yeah, look, it looks very much, I mean, even the top of the page gives one the feeling that this is the crank at 11.
Right. So, yeah, I just wanted to point out there could be stuff buried in these.
Yes.
calculations.
I have no doubt that there's stuff buried in there.
So I don't know if anybody's.
I haven't dug that deeply.
Okay.
Generally, most things that I have gotten out of this notebook involve an equal sign. There are no equal signs on any of these pages.
Well, there are some, with the thing with the 7, there's a left-hand side of the equal sign, but there's no right-hand side.
Yeah, well, okay. Yeah, that's right.
Anyway, just thought I'd point it out.
Thank you. That's very interesting.
Yeah, fascinating. How did you find this, Frank? Are you just reading the pages right now, or?
I just occasionally flip through the cost notebooks. See something.
I guess you've been preparing all your lectures for CGMS and thinking about instructions a lot.
I just. Anyway, just suggest anyone should look at these, even though these calculations are messed, there's probably something still very.
Great. Well, first proposed open problem for the day. We'll have some more later. And I want to ask George also. So George has, I mentioned, we're doing the conference proceedings, and anyone's welcome to submit. And George has graciously agreed to write a survey on the history of the last 100 years of Mach theta functions. And so I wanted to ask this story that you have here of how Ramanujan may have discovered these things. Is that published yet, or will you put that in the survey?
Yes. So basically, Ken and I and a few others had a conference at the Royal Society where I didn't talk about this, and this was in 2019, but I did write this up as a paper, so it appears in the Philosophical Transactions of the Royal Society.
Great. All right. Any other questions? Well, if not, let's thank George again.
Yep.
And well, George, I don't think you'll